Okay, guys, I'm not here for 7th period because I've got my volleyball playoff game that I've got to go to, and so I need to record this in a hurry and get this out to you guys for 7th period so you guys can watch for your homework tonight. We are dealing with center of mass, and we can talk about the center of mass as something. So if we have like large objects or a system of objects, we're going to talk about this as a location in space where we can consider all of our mass to be concentrated. So let's imagine we've got our x-axis here, and we've got a bunch of masses on this. We've got a mass 1 and a little one here, and we've got a big one over here, and a smaller one here. Okay, and you can and these all being on the x-axis, you can kind of surmise that our center of mass is going to be closer to the larger objects, which are going to be these guys over here. And so the way we mark this is we draw a circle with a plus in it, and we shade the alternate. Now, you might have seen that before, and if you see that in other things, this is what it means, and that means that that point is the center of mass. And this is, I probably wouldn't, it's probably not even in the right spot. I would say the center mass of the system actually happens to be inside this big one. So it's going to be something like there, even with these masses on either side. So here's mass 1, and mass 2, and mass 3, and mass 4. Well, this place right here, okay, is the average. We're going to call this the average location of mass. That's what the center of mass means. Center of mass is really the weighted, it's the average position of all the masses. So we take, the way we find this, the position of this, at least in the x direction, the x position of our center of mass is going to equal, and this just gets long and messy, but we have ways of dealing with long and messy things when we start getting into our math here. But here's mass 1 times the position of mass 1 plus mass 2 times the position of mass 2 plus mass 3 times the position of mass 3 and mass 4 times the position of mass 4. And so we have this weighted, in fact that's where this comes from, this is a weighted average of these, these 4 masses. That would be the weight, and then this would be the value along the x-axis of those. So that would be the other thing we're averaging. But then if we divide all of this by the total mass, M1 plus M2 plus M3 plus M4, okay, and this could go so on and so forth if we wanted to. Okay, this is how we would find the center of mass of any particular system. It's just a weighted average of the position of all of the masses. Now, take for example Pluto. Okay, no, yes, Pluto's a planet. No, Pluto's not a planet. Whichever, that doesn't really matter right now. The point is though that Pluto actually has a moon next to it, and the moon is significantly massive compared to the actual mass of Pluto. That they're very close in mass, to the point where they orbit each other on a place that is physically outside the actual planet itself. So here's, we have Pluto here, and here's Charon, which is the name of, that's the name of its moon. Okay, or its other, its co-orbiting object. The center mass of the system is actually just slightly outside of Pluto, and so these two orbit around, or they revolve around that particular point in their orbit. Okay, so we can find these things out. The Earth-Moon system, causes a little bit of wobble in our orbit because we orbit around the center of mass of the two systems. However, because we have this fluid surface on the Earth, that the water itself will actually readjust itself so that to offset the center of mass, and that is a big reason why we have tides. And the water on the Earth actually stabilizes the Earth-Moon system orbit so that we don't experience very much wobble at all. But the water itself does the orbiting, does the adjustment rather than the wobble of the orbit. So that's actually a pretty cool physical property right there. All right, so we have another way of writing this, and so the exposition of our center of mass is really equal to, well, it's the sum of all the masses times all of their positions over the sum of the masses. Okay, or another way we can write this is it's the sum of mi xi over this big M, which is the total mass of the system. All right, well, that leads us to, well, we can start breaking this up, because the center of mass, the position of the center of mass, is actually a vector. And we can start writing this. We can do the same calculation for the y center of mass, which would be the center of mass times the y over m, and the z center of mass, they wouldn't actually be equal to each other. The z center of mass equals the sum of the masses in the with the z positions all over the total mass. Well, this gives us a xyz of the center of mass. But if we have these three coordinates, we can list this in another way, and this would of course be our vector for our center of mass, and that's how that we would have this position vector for whatever it is, and it is it's xcm I hat plus ycm j hat plus zcm k hat, and that's going to give us this r vector. So so imagine we have in our field here, we've got a mass 1, and we have a little mass 2 over here, and we've got a bigger one over here, and we have a tiny one over here. All right, and all of these have their own position vectors next to them. And so what this really winds up being is that the center of mass, the r, cm equals the sum of the individual masses times their vector over the total. And this is the same thing as that. Oh, I didn't draw that very well. For you. So we have that going on. Okay, so we can use these equations if we have discrete particles. Okay, or something we can represent as a sum. That if we have, a whole bunch of different pieces to it. So I'm going to give you an example here of an extended body that we're going to do. So here's. Okay, so we have an example of an extended. Okay, example of an extended body. So let's say we draw a. We've got something that looks kind of like this L-shaped rectangular piece. Like, say it's a piece of sheet metal that we want to cut out in a particular form. We want to be able to find its. We want to find out its center of mass. Well, we can divide this into two pieces. Okay, and if this whole thing is uniformly, if it has a uniform composition to it, then we can divide this up into 8 pieces, and if we find that have actual known centers of mass, so that we could have, okay, so that would be, R1, and then that would be R2, and then we could add them together. Now, this is actually a useful property because now we can surmise that our center of mass is going to be somewhere in here. Just from experience, we can kind of tell that. But But this actually has a pretty cool use to it. Say, if we move the center of mass off a little bit, it's going to create a wobble, and you're going to it's going to have a vibration. Well, that concept is used in your cell phones. So when you have a little mass inside your cell phone that will spin, and because it is attached to its casing just off the center of mass, it's going to vibrate. And so whenever you get the buzz in your pocket, and you feel, or whenever you guys put your phone on your desk and hear a buzz, then the center of mass, okay, does have this little device in there that's wobbling because it's rotating around its off center. Its axis is held to a place that's off the center of mass, and that's what causes your phone to vibrate. Yeah, so that's really pretty cool. Sometimes it's good, sometimes it's bad. If you put the axle to your wheel off of the center of mass, you're going to have a pretty nasty vibration when you're driving down the road. So you want, sometimes, as I said, sometimes it's good, sometimes it's not so good to have your axis of rotation off the center of mass. All right, now we have other, so this is just going to be, the sum of mass times R1, or it's going to be some of that. It's just going to be mass times R1, plus mass 2 times R2. Okay, and then, divided by the total mass, and that's going to give you your, your R of your center of mass. Okay, but what if we have a different one? What if we have something that looks like this? What if we have what if we have that? Now we can kind of surmise, again, that here's going to be our center of mass, about right there. But that's just eyeballing it. We need to be able to calculate it exactly. So if we're going to drill it, we want to be able to nail that spot. So here's how it works. Okay, this whole thing can be divided up into a whole bunch of little masses. Okay, where this, of course, right here is our dx, and we have, okay, we've got this distance here, okay, is going to be our x, and then we have this distance here, which is going to be our y, but this y we can solve as a function of x. So in this particular case, okay, well, we're going to be able to, let me give you a better example. So we have a more nondescript object here. It looks like it's going to have a center of mass about there. Okay, and this is going to be made up of a whole bunch of little pieces, and we're going to have this little square right here. We'll zoom in on it. Alright, so what do we have right here? This is going to be our dm. It's going to be our differential particle of mass. And so from this, you can probably imagine what's going to happen here, that if we're moving through all of our dimensions, then we're going to be able to find the position of our center of mass, okay, is going to equal, well, we know that we're always dividing by the total mass, but this is going to be the integral then of the individual positions times their masses. Okay, so, but this is an issue here, because this is position and this is mass. So either we need to find our position in terms of the mass, or we need to find our mass in terms of the position. And this is where we come up to our concept of density. So, let's get in a little bit closer. Okay, density then is, okay, we have three different kinds. We have, the one we're most familiar with, you get it in chemistry all the time, is our volume density. Okay, and our volume density is given by the letter rho. Okay, Greek letter rho. And this is equal to our mass divided by our volume. Okay, and this is going to give us units of kilograms per meters cubed. Now we have two other types. We have area density. Okay, and this is given by sigma, a lowercase sigma, and that equals our mass over our area, or kilogram per meter squared. Okay, and then we have a linear density, which is given by a lambda, okay, not to be confused with wavelength, okay, and that's going to equal our mass over our length, or kilograms per meter. Now, you can imagine situations where this might be more useful. Let's say if we have a volume density, that's going to be the general solution. But if you have something that is of uniform thickness, if it's of uniform thickness, but it's just flat, and it's kind of a two-dimensional-ish object, like say a piece of sheet metal, or or wood, or plywood that's pretty much uniform density across. It's just flat. Then area density makes more sense, because we're going to be calculating how much mass we have for any particular unit of flat space. Or if you're measuring, say, metal rods or PVC pipe or something like that, where it's still uniform, but it's all the same in two dimensions. Say it has the cross-sectional area is the same as we go through it, then what you're really worried about is your mass per unit of length. So if we're, linear density is going to come along, and there's another way. We're going to have another density here. It's going to be charge density. Boy, we're coming up on that pretty quick, aren't we? That will have other forms of density, but these are the ones primarily for our center of mass. Linear density is actually going to be useful for us a number of times. Okay, so this is the idea, but I'm going to give you guys a couple of examples to show you really how we use this. So, so this is how we do it. All right. So the first thing I'm going to give you is example. It's example number 14 on page 273. All right, so if we're given, okay, in fact, this is a classic. This was, when I was back in San Diego, we had I was on the College Bowl team down in San Diego, and we had, essentially it's team trivia at the collegiate level, and I had a whole bunch of my physics major friends, and we got together and we created our team, and it was all guys. And so our team name was rod of mass M and length L, and that was our team name, because it's an inside joke, because you always have that sort of terminology when you take your college physics class. So here we actually have a rod that is along the x-axis of uniform density, has mass M and length L. All right, so there it is. What we want to find, our center of mass. Well, what we're going to do is we're going to find the terms of, what we're going to need here is we have this little segment right there. This is our dl, okay, or dx I should say, because it's along the x-axis, our dx. And I need to pause for a second. Okay, so here's our dx, and remember, we need to be able to come up with some sort of way of relating our mass in terms of our integrating variable. So in this case, what we're going to have here, we're going to solve Sometimes it takes a long time to focus, doesn't it? Wowzers. Alright. So we're going to solve for the position equals 1 over m, big M, total mass, r dm. But in this case, our dm is going to equal our density times our differential. Okay, so in this case, it's going to be our density of this. Well, it's all uniform as we go along. Except my drawing isn't exactly uniform, but you get the point. Is going to be our total mass over our length, and that's what's going to be our lambda, right? Our lambda linear density is big M over L, and so if we multiply our lambda times a little teeny tiny bit of length, okay, which would be dr, that's going to equal our dm. So our teeny tiny bit of mass is going to equal our density times our teeny tiny little bit of length. In fact, not dx, we're going to call that dr. It's going to be dx. So we come down here. Okay, then we know that our 1 over total m is going to equal x times dm. But what did dm become? dm is m over L dx. So we get 1 over m integral of x times m over L dx. Well, then now we can just start canceling things. So, so our m here is going to cancel with our m here. And we can move the L out front, so it's going to be 1 over our length. The integral from 0 to L, because that's how long the thing is, times x dx. Now we'll keep going with this. So at this point we can solve. So it's 1 over L. Then we have times 1/2 x squared from 0 to L, and we get L squared over 2L minus 0, which equals L over 2. Okay, which, however, we knew just by looking at the problem. We could figure out that it's uniform and it's long, and so where's the center mass? It's going to be right in the middle because there's no change of the density. However, this is the process. I didn't show you all that. This is the process for how we get, how we get there. This is, okay. So when things start getting complicated, like for the triangle that we had before, okay, we're going to have our next one, which is example 15. Also on the next page, page 274. Okay, I'm doing your homework for you, I believe. Okay, given that we have this shape, this triangle, we want to find the center of mass of our triangle. Triangle is length A, sides A and B. We want to find, okay, our center of mass. Alright, so it's going to be in here somewhere. But we just want to find the x value of the center of mass, because finding the b would just be redundant in the other direction. So what we have here is, this is our dm. Okay, our total mass is m. Now we'll get, this whole thing has a mass of m. Alright, we want to solve okay, but if we're just looking for the x direction, then we just want x cm equals 1 over m integral of x dm. Well, this has an irregular shape, but we have a way of determining what how this line is going to move, because our DM is going to change as this line moves. And what we really have here is this line is y equals b over a, because that point right there is just the slope, right? BA over x, and there is our how we're going to relate the two. So, our sigma, because we're going to find the area of this, sigma, which is our area density, is going to equal, our mass, because remember it equals mass over, back on the previous page, over here. Area density is the mass divided by the area of our thing here. So, well, what's the area of our triangle right here? Well, it's going to be 1/2 a times b. So a b over 2. That's going to simplify to 2m over a b, and that's what our sigma equals. So our dm is going to equal 2m over ab times, and what's our differential? Well, the value is going to go up, so this is sigma, and this is what our y is going to be, so it's going to be times b over a x dx. Well, then we can start canceling stuff. B is going to cancel there, that's going to be an a squared, so all this is going to plug into, this is what dm equals, that's going to go in here. Alright, so let's do 1 over m times x times our dm, which is 2m over a squared, and another x dx. All right, that gives us Okay, 1 over m. Actually, the m's can cancel. That m's going to cancel with that m, so we don't need that anymore. Okay, we can pull our constants out, so that's going to be 2 over a squared. Okay, integral of x squared dx. Okay, well, that becomes all right, we evaluate that to a, and it's going to become 2a cubed over 3a squared minus 0. And our a's are going to cancel, and we wind up with our position of the center of mass equals 2a over 3. Which kind of makes sense when you start thinking about triangles and how the massive portion gets it grows down there, and triangles have that the 3 related to it. So that's how we work out our center of mass, and that should be enough to get you guys going on your assignment. Your assignment is on Edmodo, and that's what I want you guys working on in class. And we will hit the take-home test on Friday. And that's it. Signing off.